Hello maths fans! The second model of disease spread that we're going to be looking at is that of travelling waves. You might be thinking, why are we talking about waves in this particular context? And the picture to have in mind is one of a wave of illness spreading and moving through a population. Mathematically, a wave is something that propagates with a constant shape and moves with a constant speed. And solutions of this form are called travelling wave solutions. These travelling wave solutions appear in our models by adding in spatial dependence. In other words, we want to allow people to move around within our model and within our epidemic scenario. In the SIR model I talked about previously, we only had time dependence for our three variables. And you can see this because in each equation we had only a time derivative. So we were looking at how those populations changed over time. What we want to do now is allow the populations to also change in space because people might start to move around. So what we're doing is creating a slightly more realistic model. Our starting point is going to be the same SIR model that we've looked at before. So if we remember, we had three different equations for the three compartments of our population. We had S, the susceptibles, those who could still catch the disease. We had I for the infectives, those who currently have the disease and are spreading it through the population. And R for the recovered category, which are those who have caught the disease and either died or recovered and are now immune. The model gave us three differential equations for each of the three populations. So starting with the susceptibles, S, we had that ds by dt, the rate of change over time of the number of susceptibles, was equal to minus some rate of transmission, R, times the number of infectives multiplied by S, the number of susceptibles. And remember, we had these two terms here because the disease was transmitted between populations, between the susceptibles and infectives, through contact. So very similar to what we're seeing at the moment with COVID-19. Our second equation was for the number of infectives. And again, the time rate of change of the number of infectives, di by dt. So now this increased by this same factor of RIS as people caught the disease. But we also saw that this decreased due to some rate of recovery or death, which we labeled with A, times the number of infectives, I. And then our third and final equation for the recovered population, R, told us that the rate of change over time of the recovered population was this recovery or death rate A multiplied by I. And this one, of course, is positive because the R population is growing in this instance. Since we're introducing spatial dependence to our original SIR model, we need to make some additional assumptions that explain how people interact with the space around them. So our first assumption is going to be that the susceptibles, the S population, are not going to move. So in the context of the current COVID-19 outbreak, you can think of assumption one as saying that people susceptible to the disease stay at home. The second assumption is going to be about the movement of the infectives. So people that are infective are indeed going to move. And we're going to say that the infectives migrate at a constant rate. The third and final assumption is going to be about the removed population. And again, we say that once you're in the removed population, you again don't move. So in summary, all of the spatial dependence is really focused on the infectives in assumption number 2 here. The susceptibles don't move, they stay at home. The removed population also doesn't move. And we're really interested in how those who have the disease and can infect others are going to migrate and spread the disease through the population. What this means for our equations is that we have an additional term in the second equation, this di by dt equation from the original SIR model. So we add in this term which has a constant d, so this is going to be our constant rate of diffusion. And then the way we're going to model the diffusion mathematically is with a derivative. So we say that we have a second derivative of I with respect to x. Because our populations now depend on both time and space, this is why we have a partial derivative in this formula over here. And so I'm going to do the same and convert these derivatives into curly letter d's. And this is what signifies that it's a partial derivative and that our functions or our variables s, I, and r now depend on both time and space. To begin to analyze the equations, we first do something called non-dimensionalization. The details here are not that important, but the key idea is to take all of the constants that are in our equations and then combine them in such a way that we get one key parameter. And when we do this, we actually see that the parameter that appears is this reproductive number R0 that we saw in the first video about the basic SIR model. The basic reproductive number R0 gives the number of secondary infections that we expect to happen on average in the population from a single primary infection. So in other words, it's the number of people that you expect one infected individual to pass the disease onto. And we define this mathematically as R0 is equal to the initial susceptible population S0 multiplied by the contact ratio Q. The contact ratio Q itself is equal to R divided by A, where R and A are the numbers over here in our model. And it is defined to be the fraction of the population that comes into contact with an infected individual during their period of infectiousness. As well as non-dimensionalizing, we use a second mathematical trick, which is to change variables. So at the moment, we have our three populations, S, I, and R, which all depend on time t and space x. And what we want to do is create a new variable, which we're going to call y, and then we're going to convert these equations into differential equations just involving this one new variable, which is given by x minus a constant c times time. And making this change of variables is going to really simplify our set of equations. As you can see, our equations have changed quite dramatically. So we no longer have derivatives in terms of x and t with partial or curly d's. We've gone back to full derivatives in terms of just our single variable y, where remember y is x minus c times t. You'll also notice that we only now have two equations. The equation for r hasn't vanished. I've just decided to ignore it for now, and we can come back to it later if we really want to know about the recovered population. Once again, we find ourselves wanting to solve a set of differential equations, which means we need some boundary or initial conditions. So what we do here is we go backwards in time to before the start of the epidemic. So if we let time here go to minus infinity, which means going back into the past, then y is actually going to go to plus infinity because of this minus sign. So going all the way back to the past, so time's going to minus infinity, which because of this minus, remember, means y goes to plus infinity, then we must have that the number of infectives must go to 0, because this is a time before the disease even existed in the population. It's before the disease outbreak occurred. So we have 0 infectives going backwards in time. And we also have that the susceptibles, S, must go to the initial susceptible population. In the first SIR model that we looked at, this initial susceptible population we labeled S0. But since we've done a non-dimensionalization, What we've actually done is convert Ri and S from being full population numbers into now being population ratios, or the proportions of a specific given population. So for S to go back to the initial susceptible population S0, in the non-dimensional model, that means S must go to 1. We can also think about what we expect to happen in the future. So the future here is when we let time t go to infinity. And that is going to make y go to minus infinity because of this negative sign. So as y goes to minus infinity, then the outbreak must have passed. So really far down in the future, the disease has come in, it's spread through the population, and now it's disappeared once again. So as y goes to minus infinity, which is the future, we must also have that I goes to 0. Now we don't yet know the value of S in the future. That's something we're going to want to find out, which is what we're going to do when we start to explore the model a little bit further in the next steps. The first question that we might want to know the answer to is going to be how fast the disease is going to spread through the population. Because we're now picturing the disease as a wave propagating through the population and spreading the illness, we can calculate the wave speed, and that will tell us the speed of the spread of the disease in our outbreak. So this is going to be question 1. To answer this question, we use a clever tool called linearization. I'm not going to go through all of the details, but the basic idea is that we use the value of S in the past to make an approximation. So as we go into the past, y goes to infinity, S is going to 1. And so what we do is we say that S is equal to 1 minus p, where this term p is going to be small. It's an approximation. And then, because we are linearizing, this is telling us that we want to substitute this into our equations and ignore any terms which are p squared and higher. We now have the set of equations here in blue, which, whilst it might not look necessarily any simpler, it's now in a form that allows us to use another mathematical tool. This one is called phase plane analysis, and applying phase plane analysis to these two equations actually tells us that for traveling wave solutions to exist, then we must have that c is greater than or equal to 2 times the square root of 1 minus 1 over the reproductive number R0. And this expression, it turns out, is actually the minimum possible wave speed for there to be a traveling wave solution to this entire problem. And with just a little bit more work, you can show that not only is this the minimum required wave speed for a traveling wave solution to exist, but typically the wave speed itself is given by this minimum value. So the value c, which appeared down here in our change of variables formula, is actually the speed of our traveling wave, and therefore is the speed of the spread of the disease as it propagates through our population. In any epidemic, but in particular for the current COVID-19 outbreak, we want to make this speed of the disease spread as small as possible. We want to slow down the propagation of the disease through the population. And looking at this formula, we can make c small by making R0 also small, because we're subtracting here the number 1 divided by R0. So if we make R0 small, we subtract off a larger and larger number. So you might be thinking, what happens when c goes negative? Which could happen if R0 was small enough. Now this actually cannot happen in the case of an epidemic, which is what we're considering here. Because we saw in our first basic SIR model that an epidemic will occur provided R0, the basic reproductive number, is greater than 1. So the absolute smallest value that R0 can be is 1. And when you substitute in R0 equals 1 into this expression, that gives you C equals 0. So whilst we want to make R0 as small as possible to lower the speed of the spread of the disease, the minimum value we can get it down to is just above 1. And to do that, we look down at our formula and see that the only thing we can control here is the contact ratio Q. The number of susceptibles S0, this is fixed. This is pretty much everybody for COVID-19 because it's never been around before, so we can all catch it. We are all susceptible to this brand new disease, but we can lower the contact ratio. So Q, remember, the contact ratio is the fraction of the population that comes into contact with an infected individual during their period of infectiousness. So to lower the contact ratio Q, we, number one, wash our hands all of the time. Number two, we stay at home as much as possible. And number three, if we do have to go outside, we minimize contact through social distancing. Another question we might want to know the answer to is, what is the severity of the epidemic? So we did something similar in our first video about the original SIR model, and we saw that the key parameter, or the key thing we needed to calculate, was the number of susceptibles left at the end of the epidemic. Because if we know the number of people left at the end who have been unaffected by the disease, then this will actually tell us how many people have been affected by the disease and therefore how severe the epidemic was, because we know the total population must be equal to the two components added together. So the thing we want to know here is, what is the value of S end, which in our boundary conditions, we want to know S at minus infinity because we want to go into the future. So here, what we want to do is take the top equation and this term here for IS, and then substitute, because this is equal to C times the S by dy. So we want to take that and substitute it into here in our second equation. Because when we do that, our second equation now has y derivatives on every term, and so we can integrate the whole equation and get a nice neat expression involving I and S. Having made the substitution and done the integration, we get the following equation: di by dy plus c times I plus c multiplied by s minus 1 over r0 log s is equal to a constant. And to calculate the value of the constant, we have to use our initial or boundary conditions. So here, if we go back to the past, so we let y go to infinity, then I must go to 0, and so the derivative di by dy will also go to 0, and s will go to 1. So if we substitute those values in here, this gives you the value C. To get the number of susceptibles left at the end of the outbreak, and therefore know the severity of the epidemic, we need to let time go to infinity. We need to go into the future. So this tells us that I goes to 0, so we're going to lose the di by dy term and the I term here, and then the S term will go to our value S end, which is what we want to know. So this equation at the bottom of the board, Sn minus 1 over R0 log of Sn equal to 1, gives us an implicit equation which we need to solve for S end. Like we've seen before, the best way to deal with these implicit equations is to plot a graph to try to understand what's going on and the relationship between S end and R0. Now, before I do that, it's worth thinking about the range of values that S end and R0 can possibly take. So because we've been considering this non-dimensionalized model, we saw earlier that this means that S is actually a proportion of the initial susceptible population. and so it can only vary between 0 and 1. We also have some restrictions on the value of R0. So we saw here, when we were discussing the travelling wave speed and the speed of spread of the disease, that R0, remember, has to be greater than 1 if there's to be an epidemic in the first place. Since we are modelling the spread of an epidemic, this means that R0 must also be bounded by 1. If I now plot the graph, what we see is a curve that rapidly decreases like so. So we have this maximum value for S end being 1, which means nobody caught the disease. The susceptible population at the end of the outbreak is identical to the number of susceptibles at the very beginning. This is the best case scenario that you can hope for in any epidemic. And from this maximum value of 1, we see that Sn starts to decrease as the value of R0 increases further and further. So to go back to our question about what is the severity of the epidemic, we said that the total number of people who catch the disease will be lower if the number of people unaffected, or the number of susceptibles left at the end, is as large as possible. So we want to make S end as big as possible by varying R0. And so on our graph, it's very clear that to do this, we want to make R0 as small as we can. So here, that means making R0 as close to 1 as possible. And the way to do that is to reduce the contact ratio Q. We're back in the same position that we've been in 3 or 4 times before. It all comes down to reducing the value of Q. So washing your hands, staying at home, and if you have to go out, practice social distancing. So in summary, using our travelling wave model for the spread of a disease, we've been able to derive an equation for the wave speed, which remember is the speed at which the disease will spread through the population. And we've also been able to get this equation at the bottom, which determines the number of susceptible people left at the end of the outbreak. Now, to minimize the severity and the impact of an outbreak such as the current one with COVID-19, what we want to do is to lower the wave speed as much as possible, make the disease spread as slowly as possible to give us more time to try to come up with measures to combat it, such as vaccines. And to do this, we saw that we want to make R0 as small as we can, where the lower bound for R0 is 1. So to get R0 down to 1, we go to our formula over here, which tells us that R0 is the contact ratio Q times S0, and so to make R0 small and reduce the speed of the spread of the disease, we want to lower the contact ratio Q. Then for our second question about the severity of the epidemic, we got this equation for the number of susceptibles at the end, and we want to make this as large as possible, because the number of susceptibles left at the end of the outbreak tells us the number of people who have been unaffected by the disease, and so they haven't caught the disease. So we want to make S end as large as possible. So considering the graph over here, we saw that S end has a maximum of 1, and we can get closer and closer to that maximum by again making R0 as close to 1, as small as possible. And this was once again done by reducing the contact ratio Q. Now I know I keep banging the same drum telling you we've got to lower this contact ratio Q, but the fact that it keeps coming up in all of these models is actually really good news, because it gives us one specific parameter that we want to make as small as possible. And this is the power of mathematical modeling, because even here, when we introduce spatial dependence into the SIR model from the first video, we get different solutions. They now look like traveling waves. But all of the things we want to happen, a slower spread of the disease, fewer people getting the disease, all of these things have the same thing in common. They are all reduced by making the contact ratio Q as small as possible. So this is why all of the measures, washing your hands, staying at home where possible, and if you have to go out, practicing social distancing, all of these measures are designed to reduce the contact ratio and to help us try to control the spread of COVID-19. Thank you everyone for watching. Please do remember to subscribe to my channel if you've enjoyed this video, and I'll be back soon with some more maths. Take care.